All right, so 12.3, the tangent line problem, okay? So we're gonna talk about a tangent line. Now there's gonna be a lot of like extra writing in here. That's gonna be for you to like go back and kind of process, read through on your own. There's gonna be very textbook defined definitions that we're gonna try our best to paraphrase, okay? All right. So our goals for this are to do these things: understand the tangent line problem, use the tangent line to approximate the slope of a point, use the limit to define the slope, and yeah. So tangent line to a graph. So our first section is, what is the tangent line to a graph? Well, that's the line that best approximates the slope of the graph at a point, okay? That's at a point. Notice it's not 2 points with the slope. It is at a point, okay? To determine the rate at which a graph rises or falls at a single point, you can find the slope of the tangent line. Bless you. Thank you, sticking with you. No, y'all have cleared me out. Y'all have cleared me out. Collectively. Okay. All right. So main thing, tangent line approximates slope at a point. Bam. That's tangent line. And when we're calculating slope, it's the rate of change. How is it rising and falling, right? Rise over run. Sounds familiar? Yes. Okay. Now, this is all the same, all together, exact same thing, except emphasizing that we've been finding the slope of just lines, like just of linears, correct? All right. You can find the slope of anything at a given point. It's not just linears, it's the slope of anything. So for example, if you look at this parabola, we have 4 points marked out on this parabola, and I can find a slope at each given point on this parabola. Okay. And that is what the tangent line is. At this specific point, what is the line, the slope of the line that specifically only touches this one point on the graph? Okay. That's what your tangent line is asking you. Your tangent line can have a positive slope, a negative slope, or a constant slope. If it's constant, that means I have a slope of 0, right? If I'm a constant, the slope is going to be 0, okay? Horizontal lines have a slope of 0. Vertical lines have a slope that is undefined. All right. So here you can even go back to geometry and talk about it in terms of a circle and finding one point on a circle. And going around. So tangent to a circle, does that ring a bell from geometry where y'all talk about the tangent to the circle and using that and a secant to a circle and all those things you can do with a circle in geometry. All right. So now we're into the slope of a graph. So we're not going to write all this. We're going to summarize it. Basically, it's saying is that you can approximate the slope at a point by drawing on the graph. Okay, that's what this whole thing is telling you. The key thing is that it is a approximation. With me drawing the slope at the point, it's going to be an approximation, not an exact. It's going to be what? Approximation. Drawing the slope is an approximation. See how we summarize that? In calculus, you should end up doing, what is the mapping with slopes called? Can't think of the name, drawing blanks. But basically, you're going to find the slope of a function at many points, and you're going to mark it out. And after you mark it out, you'll end up seeing what its derivative looks like by finding that repeated slope. I had a brain fart. All right, so again, slope of the graph is what we're talking about, and we're talking about approximating it. So for example here, if I have the parent function f of x equals x squared, and I graph it, boom, there's my parent function, and I go to the point 1, 1, and I want to approximate the slope here. I'm going to draw a very careful, real straight line, because you know my lines are really never straight. I admit it out loud. But you're going to draw a perfectly straight line that only touches that point and analyze that line. Okay, so you're asking yourself, what is the slope of this line that only touches this point? That's what your tangent is asking you. Does that make sense? So what is the slope of the line that only touches this point? So I can estimate, well, this line I run 1 and I rise 2 to get to another point, right? So therefore, I'm approximating the slope to be 2, right? Rise over run. Okay, that's because our slope again is our change in our y over our change in our x. That's what the rise over run helps us remember. And we had 2 over 1, which makes it 2. Again, this is a what? Approximation. I use the quadratic parent function because it's actually pretty easy to do it on there. And that is actually the slope at that point because it's a pretty easy graph to draw and connect.
So is for the H, the one with the H on it? Is
The
that
limit.
just that, but your H is your difference in X, meaning your difference in X is versus 0.
Yes. So yes, we're gonna look at it from there. All right, so that's how that works. And again, this is tangent to the point there. So Sam skipped ahead and we're gonna talk about how that ties into the difference quotient. Okay, so tying that into the difference quotient, your secant line. So your secant line is how we would normally find a slope of a line by approximation. That meaning that we just choose another point on our function to the point that we want and we approximate their slope, right? But we're using points on the line. That makes it a secant line because they're both on the function. Okay, there's 2 points and they're both on the function and we're approximating their slope between each other. Okay, that's what the secant line is. Now, difference quotient allows us to use only 1 point and find the more accurate slope from that point. And what is our difference quotient again? It is this. But to find our slope, it's the limit of the difference quotient as it approaches 0. And that's what this is telling you. Your slope of your sequent, the slope of your secant, the limit of the slope of your sequent equals the limit of the difference quotient. And that's the main takeaway there. So for us right now, the limit as h goes to 0 of f of x plus h minus f of x divided by h is our bread and butter. Okay. What people realize using this difference quotient over and over, they were able to create rules for what you will later be known as a derivative. Okay. All right. So what Sam was saying was, is what's happening with the difference quotient, is one, you're changing your y over you're changing your x, and the answer is yes. So if you look right here, our change in our y, that's the numerator of our difference quotient. Our h, our run here, that's the denominator of our difference quotient. Okay, so as this value gets closer and closer and closer, as this value gets smaller and smaller and smaller, and we get closer to here, we're going to end up finding our tangent. So here's a visualization of that. So the closer and closer this gets, closer and closer to the original point that I want, what's happening? My secant is going from being a secant to becoming a tangent line. And that's why it's what is the limit? What is it approaching as it gets closer? As your change in h gets closer to 0. And that's why it's the limit of this function. Okay. All right. So here, I think you need to write this somewhere. No, you don't. I lied. All right. So here we go. We're going to fix this. So on your example, it says that it should be, instead of 3 comma negative what, it should be 3 comma 14. That is a typo made by the textbook people. All right, and we're going to go through and find the limit. We're going to use a limit to find the slope of this function at the given point. So the first thing we're going to do is go ahead and set it up. So we have the limit as h goes to 0 of f of x plus h minus f of x all over h. Okay. They give us what our x is, and what is our x value? 3. So everywhere there's an x, I'm going to plug in a 3. So we have f of 3 plus h minus f of 3 all over h. Okay? How do we feel so far? Questions, comments, concerns with people who are actually taking notes and paying attention? It's cool. All right, so we're gonna substitute in for x. So we have parentheses 3 plus h squared plus 5 minus, well, what is f of 3? 14. We know the value of 3 of this function. It's gonna be 14 all over h. We already did this before, 3 plus h squared, and it came out to be 9 plus 6h plus h squared plus 5 minus 14 all over h. Well, 9 and 5 make what? 14. So what happens to the negative 14? Cancels. And what are we left with? Over h. What can I factor out? I'm a lazy factor, so I usually just cross them out. I actually don't write the whole thing. And so what's left standing is 6 plus h. So now I'm looking for what is the limit as 6 plus h as h goes to 0. And what do we get? 6. So our limit is 6. So the slope at this point would be 6. So what that means as far as a graph, oh, go back. So the parent function just moved up 5, right? Transformation of 5. I look something like that. And guys, I'm gonna do my very darnest to draw the best line you've ever seen, okay? Okay, so this is gonna be 314. At 314, I would have a slope of 6, right? So that I can have a point going the other way. I'm gonna go down. So if I'm here at 14 and I come down 6, that's gonna put me at what? 14 minus 6, 8. It's gonna put me somewhere at 8. And I go over 1, it's gonna put me somewhere in here or here. This is not drawing to scale, guys. At all. Dang it, it's not gonna work. I can't draw. I thought I could. I had faith and hope in myself, but I think my graph needs to be wider. I know. We thought Miss Jones was gonna draw a straight line. We thought wrong, she failed. Okay, let's try again. I'm not a quitter. Make you here. That's the best I got. That's the best I got. That's all I got for you. And it barely went through. But that's where it's at. That would be roughly where it's at. If I had graph paper, it would have been better. If I did it on a ruler, but that would be the slope of that. Okay. And that's what you need to be able to do. So just really quick, I would like you to try it for just x squared. Yes. You can do it in the top right corner of your notes. Yes.
No,
So for
we don't put down, say no sometimes. No.
Oh.
So did you say positive or negative? Okay, I didn't see that. I didn't see that part. Oh, didn't see that part.
Why did it go?
It went to sleep. And I haven't clicked on it again.
This goes on sometimes.
I know. Hey, they have like supposed to have some of the best working atmosphere. Amazon,
Yeah,
Google. Like Amazon the building, not Amazon distribution, like Amazon corporate. Yeah, not Amazon. No, my niece is right there. And I've seen their TikToks at work. So,
Yeah, super.
Yeah, you think we-
no, my nieces work at Amazon distribution and they just make TikToks and sort stuff.
Super nice.
Literally. All right, okay. Let's check and see what we're doing. So the first thing you want to do is, since we're at -2, we're gonna plug in -2, right? And then I'm gonna evaluate at -2. So I substitute -2 plus h into the equation and -2 squared. And after I evaluate at those 2 points, I'm left with 4 minus 4h plus h squared minus 4. What goes away? Initially, the 4s. I have a +4 and a -4, and they can eliminate. So bye-bye. Okay, and I'm left with -4h plus h squared divided by h. Now what can I take away? The h's. So I can get rid of the h's. And all I'm left with now is -4 plus h. And again, what does h equal?
0.
0 when we're taking the limit. So as we take the limit, as h goes to 0, we end up with
-4.
-4.
You still,
And mine is slipping.
Take off, take the back off.
I have no days. All right, so here's a better drawn picture of it. Actual drawn out for you. So here's the parent function, x squared. Here's your tangent line at -2, 4. And yeah, it has a slope of -4. Notice it's decreasing as we regress from left to right. All right, the next part is the derivative of the function. The derivative of the function is not that much different. The only difference is instead of plugging in x, we don't plug in for x. Okay, you do not plug in for x. That is what the derivative is.
So
Okay,
X stays back.
x just stays x and you evaluate. That is the gist of the derivative. Still taking the limit of the difference quotient. Okay, but we're not plugging in. What is the benefit of the derivative?
You can use it for every point.
You can use it for every point. You can now take the slope of any point. Once you have the derivative, you can take the slope of every single point.
Precisely.
Okay, that is the main goal of the derivative.
if it ain't one thing.
Okay.
it's another.
As you get better at it, first thing that you'll learn is your derivative rules. And the derivative rules are established from taking the limit of various functions using the difference quotient. Okay. All right, that is the gist of it. There's really not much to write here. The main thing that you need to take away here is this. Oh, that is not a good circle.
You can't draw one.
It was not a good circle. Okay, this is the main takeaway here. The rest is nice to know. We represent a derivative by using f prime. So you see how it says f prime of x. That's how we represent that this is the derivative, not just the function. Okay, you can take the second derivative and it'll say f double prime.
That would yeah.
The derivative. Okay. All right. So definition of the function, the derivative, this is exactly what we just wrote down. Just to remember that the derivative f prime of x is a formula for slope of a tangent line to the graph at any point. That's the takeaway. So let's do it. It's on your paper. Here's our example together. So if I want to find the derivative of this, I'm going to do the difference quotient, but I'm not substituting anything in for x. Does that make sense? So we have the limit as h goes to 0. And we have this. Remember, you have to use f of x plus h. So I'm going to have 9 minus 2 times x plus h squared minus 9 minus 2x squared all over h. Now your job is to simplify like you can't, till you can't know more, okay? So we're left with 9 minus 2 times x squared plus, my pen did that. x squared plus 2xh plus h squared minus 9 plus 2x squared. Okay, I'm going to distribute. You get a 2, you get a 2, you get a 2. So we have 9 minus 2x squared. What are they doing? Plus 4xh plus 2h squared minus 9 plus 2x squared. All right. Oh, yes. Thank you. Thank you. Thank you. Thank you. Thank you. There we go. All right. What goes away? The 9s, my 2s, and that's it. So we're left with negative 4xh minus 2h squared all over h. Okay. And then what eliminates? Your h's. After your h's are gone, you're left with your derivative equals negative 4x minus 2. And that is the derivative of 9 minus 2x squared. And that concludes 12.3.